Welcome to part 3 of the Euchre Simulator project. In part 1 I talked about what I'm trying to do, and in part 2 I reviewed how to use R to create these simulations. No disrespect intended to those two, but they're stupid and a waste of time. This is part 3, the real magic if you will. What are the conclusions from all of this work? You can watch this video in order if you want, but I'll also post a table of contents here so you can jump directly to the section of choice. I suppose if I could only save one table from this whole project, it would be this one. This table has the expected points from every combination of hand and lead. When I say every, I don't actually mean every. I didn't bother to do situations in which I have 5 trump. That I can actually figure out on my own. You should make it trump whenever you have 5 of something. I also didn't look at situations with only 1 trump because that's usually bad. The exception is the ironclad rule of Euchre known as never turn down a bower, which has its own section later in this video. So most of the action is when you have 2, 3, or 4 trump cards, and this table has all of them. So for the next 9 minutes, I will slowly scroll through this table. I'm just kidding, of course, but I am thinking of printing this on a nice-looking custom book to use during Euchre games. I casually flip to the appropriate page and chuckle about how I used to just make uneducated guesses. Relics from a more primitive time. I would do this mainly to piss off friends and family. One problem I encountered is how to summarize a mountain of data into something interpretable. This table is great, but there's way too much here to conclude anything. So what follows in this video are aggregations of this table and others into one-sentence conclusions. So here, one intuitive view is the expected points by lead. I average across all the thousands of hand combinations to see if there's any differentiation from which player starts the round. This shows that there's actually a slight advantage to having your first opponent lead, i.e. you get to play last, and to having your partner lead. Both of these make sense. Playing last is good because if it's legal, you can take the trick with the weakest possible card with no concern about the player behind you. And your partner leading is also good because a side ace or a big trump card can win without your help. I've said many times that the manner in which the decide programs are coded will impact all of the subsequent conclusions. One efficient way to check this is to look at individual boundary cases, a boundary case being an extreme example of the universe of hands. So I know how the machine will play, and this is my opportunity to see if there are any improvements on these base rules. The first one I checked is the worst 3-trump hand you can have, namely Queen 10 9 side 9 side 9. Literally the worst 3 trump cards and the worst 2 side cards. If right, left, ace, side ace is the Ferrari of 3-trump hands, then this hand would be not as good. I'm going to look at lead equals P1, which is me, to keep it simple. The base programming says if you have boss trump, lead it. If you don't, lead the strongest non-trump card. So in this instance, I created a side program that leads the Queen of Hearts instead on trick 1. Here are the results. This is a two-way table that shows how the games play out in the 2 different scenarios. The diagonal represents the number of games for which the output is the same. So in 554 of the 1,000 games, whatever number of tricks you got under the status quo strategy, you'll also get under the modified strategy. The remaining games have a different outcome. The number above the diagonal are games for which the results are better. There are 321 of those. And below the line are the games for which the modified strategy does worse. And there are 125 of those. So it looks like this change is a good thing, and that's confirmed by the overall summary. We expect to win more points and get euchred less often if we switch to leading trump on the first trick. I wasn't surprised to see this one, and it's not ideal. To maximize the value of the simulator, I would prefer to have every status quo playing pattern as optimal. That's a difficult standard to meet, so all you can do is spiral into an inferno of rage, punch a hole in the wall, and continue working the next day. Before moving on, the conclusion is, in a hand like this, leading small trump is more effective than trying the weak side card. This is the same concept, but I'm more confident in the outcome here. The boundary in this case is what a typical player would call a good, solid hand. We have right queen 9 side ace queen suited. I think we'd expect to get 1 point, maybe 2 if we're lucky. So we make it trump and have the lead. Conventional wisdom is to lead the right bower, the strongest card in the game, to start with a guaranteed trick and to deprive your opponents of a trump card. Of course, you're also depriving your partner of a trump card, so I can imagine there are some situations where leading the ace could be better. To test that, just like before, I made a side project that starts the game with the side ace rather than the right bower. The process is the same, and we can see that improvement can happen, but is rare. Both strategies are right around 1 expected point and low probabilities of being euchred. Basically, it's a pretty good hand with either approach, but leading the right bower is statistically better. Just out of curiosity, I wanted to see what the change would be if you had side king-queen rather than side ace-queen. Once again, both hands are good, but the penalty for playing the offsuit here is just a bit worse than before. That makes sense. At least in the first option, the opponent would have to play a trump card to beat the side ace. Here, the king could lose to that ace. So that outcome makes sense too. Here's where things get interesting. This is the first case in which the results sharply diverge from what I was expecting. This is the same hand as a moment ago, but now we have the left bower rather than the right bower. The conventional play, in my playing circle at least, would be to play the side ace. And that's the playing order reflected in the big table of outcomes. As before, I wondered if this was best, and made a side project that starts with the 9 of trump, kind of like in the Queen 10 9 side 9 side 9 program from a minute ago. Not only is this approach better, it's a lot better. It was so much better that I looked at some of the games that improved to see if my gameplay coding was still reasonable. So take this game for example. The second player plays the right. It's not a bad move on its face. I think a lot of players would do exactly that. One wants to avoid slightly over-trumping only to have player 3 play the left or the ace, but this isn't a forced move by any means. And here in game 13, player 3 had the king, so player 2's 10 would not have been enough. Confusing things even more, player 4 had the ace. And here's an example where not playing the right bower would have lost to the king of hearts. So I'm not sure on this one. I think ultimately leading trump with a left high 3 trump hand is probably better. I'm not sure the gap is as wide as these numbers reflect, but it feels directionally correct. I started playing like this a few weeks ago once I saw this finding, and it feels like my results have improved a bit. I keep texting my brother asking him to take diligent notes during our games. Just sends me back one finger in the air, which I'm guessing means I'm the #1 Euchre simulator in the world. I appreciate that, but honestly, I'd just rather have the notes. The final boundary case is an extremely strong hand. Looking at right-left ace, side ace shows excellent results for all leads. The result is strongest when I had the lead to start the game, and this makes sense. If someone else leads, clubs or spades could result in my side aces getting over-trumped. See how the expected points for lead equals P1 is 1.994. That means that in only 6 out of 1,000 games, I didn't get all 5 tricks. So bear with me for an unnecessary sidebar here. This case is so simple that I should be able to figure out the theoretical number without a simulator. With this hand, I start the game with 3 guaranteed tricks. Then my 2 side aces will probably win. The only way they will not win is if one of my opponents has 4 trump cards. He would need to sacrifice 3 against the right-left ace leads. Then the 4th one would be either side ace. It seems pretty unlikely, but I'm not sure if 6 out of 1,000 is too little or too much. This can be worked out with basic probability as follows. Probability of one of my opponents having 4 trump cards given my hand is the probability of the first opponent having 4 trump cards given my hand, plus the probability of the second opponent having 4 trump cards given my hand, and opponent 1 has 0 trump cards. Focusing on the first term, there's a way to do this with combinatorics, but it's been a few years, and I think I can just figure it out one card at a time. For card 1, there are 4 eligible trump cards to be selected. There are 19 total cards, 24 cards in the game minus the 5 that are already in my hand. For card 2, there are now 3 eligible trump cards to be selected. There are 18 total cards because card 1 has been filled. And continuing this, we have 4 19ths times 3 18ths times 2 17ths times 1 16th equals this number. This player has 5 cards, not 4. Any of the 5 can be the 1 non-trump card, so I have to multiply by 5. I do this and get 0.00129. So the first term is complete. The second term works much the same way. Opponent 1 now has a hand, so there are 14 eligible cards instead of 19. The math follows similarly as 4 14ths times 3 13ths times 2 12ths times 1 11th is that number. Again, we multiply by 5 because I have a 5th card that can be anything. That results in 0.005. But this is conditional on the first opponent's hand being trump-free. That hand has any trump cards. It becomes impossible for the second opponent to receive all 4. That probability is 0.2583. So term 2 is 0.0050 times 0.2583. And again, that equals 0.00129. So you can see that's the same number as the first player. So after the fact, I can say that makes sense, but I didn't think it would work out that way when I started down this path. Adding these gets to 0.00258. So we expect to get fewer than 5 tricks 2.58 times in 1,000 simulations. My simulated number was 6. It's in the ballpark, but at this point, I was sufficiently invested to wonder if my math was correct. So I ran 100 batch runs of 1,000 simulations apiece and got a distribution of outcomes as follows. The average of these numbers is 2.76 against my theoretical number of 2.58. The answer of 6 that I got is clearly on the high side of the distribution. It happened only 7 times in 100 runs. This is probably evidence that I did the math correctly, but just for the hell of it, I did another 9 iterations of the same process. The averages of all 10 of these runs are as follows. And here's a chart of outcomes across all 1,000 simulations of 1,000 hands apiece. The average across the 10 is exactly 2.58. It's kind of funny because there's no reason that has to happen, and you can see the variance is not trivial, but the simulator has precisely matched my theoretical number, so I will call that a win and move on. The sidebar is now complete, and it exemplifies the power of simulation. Even in an extremely simple case, the theoretical math still took me about an hour to do after screwing it up multiple times. Despite thinking hard about it and checking my work, I still trust the simulation more. Maybe a stronger statistician could have gotten to the right answer in 5 minutes, sure. With an average hand like right ace, 9 side, queen, as far as I know, that's impossible to do on paper in less than a week. In one of the boundary cases, I replaced a side ace-queen with king-queen, just out of curiosity. Of course, the base evaluation showed a lower expected points for the latter hand. There's nothing surprising about that. Aces are better than kings. You can generalize that concept across the universe of simulated hands. It stands to reason that aces are much better than kings are slightly better than queens, and below that the relative strength dwindles. Said another way, it's a big deal to replace an off-king with an off-ace. It's not a big deal to replace an off-9 with an off-10. That's the logical argument, at least, and I tried to corroborate this globally by using the completed simulations. Step by step, it looks like this. 1. Pick any 2 cards to compare, say side ace versus side king. 2. Find every hand that contains a side ace. 3. Determine the analogous hand by replacing the ace with a king of the same suit. 4. See if the hand has been evaluated. Note that it may not be, because some of the hands in this cohort will already have the king. For example, right queen, 9 side ace king. Compare the expected points of the analogous hands. Note that lead is a matching variable, so we compare lead equals P1, lead equals P2, lead equals P3, and lead equals P4 separately. Average across all hand pairs, and average out lead. I did that, and here are the results. In words, the conclusion is as follows. All else equal, replacing a side king with a side ace adds a third of a point to your expected outcome. Then the effect weakens as we move down the list, as we predicted a moment ago. Here's the same process, but within the trump list. Just like with the offsuits, the impact is biggest at the top. Replacing the right bower with a left bower is a big deal, but with trump, there's still a non-negligible lift for each trump card. My explanation for this is as follows. 10 of trump versus 9 of trump is a common trick-deciding matchup. Off 10 versus off 9 is not a common trick-deciding matchup. It can happen, but usually it will be overshadowed by either a stronger card of the same suit or any trump card. Ordered cards. I was excited for this one. Intuitively, we know that giving the 9 to your partner should help, giving the 9 to an opponent should hurt. Ordering the ace will do the same, but more so due to the higher rank of the card. But how impactful is it exactly? Programming this took some doing. When I was sketching this originally, I figured I wouldn't need to do every card, but rather the low side, the 9, and the high side, the ace. I quickly realized the flaw in my logic. It's the same issue as the incremental card evaluation just a minute ago. Say I have the right queen 9 of trump. There are dozens of rows with these outcomes in the base table. I want to see what happens when I give the 9 to my partner or the opponents. But there's the rub. There's only one 9 of hearts and it's in my hand. I can't imagine what my computer would have done if I tried to give the same card to 2 different people. To deal with this, I simply gave the 10. More generally, I made a low category that gives the 9 if possible, otherwise the 10 if possible, otherwise the queen if possible. And on the high side, I did the same. Ace, king, queen, in that order. To compare to the base hand, I searched for the corresponding hand with an ordered card, joined on the expected points, and summarized the output in this table. I'm a weirdo in that I prefer to see numbers rather than graphs. Everyone in my field loves data visualization, can't get enough graphs. Being the understanding person that I am, I try to accommodate this. I'm not great at data visualization, and I'm not great at R, so that's not great squared. These graphs took me a really long time. Graph 1 shows the incremental expected points by player by card. So this leftmost bar says when you give the 9 to your opponent on your left, on average, you will get 0.38 fewer points than if you had called trump with this hand without ordering the card. The next bar shows about 0.31. That means that giving the 9 to the opponent on your right won't hurt you quite as much. And then north of the line, you get a lift of about a third of a point when you give the card to your partner. Looking across the bottom section, you can see that it's always worse to give the card to the person on your left. The first reason that comes to mind is that when you do that, your partner leads the first trick of the game. That means you go third, and the opponent to whom you just gave a card goes last. So that makes sense. You've given that opponent a card that can potentially take the first trick, and the option to discard something which saves them from following suit, and you have to play before that person. Sounds reasonable, but I'm just guessing. It occurred to me that I can actually prove or disprove this, so I modified the process that counts tricks 1 per round to look at each trick individually. I took a simple representative hand, right ace, queen, side king, and compared the trick winners in the two scenarios. So the base column here represents how many of the 1,000 hands did we win a given trick. So we won the first trick 638 out of 1,000 times. But when I gave the 9 to the opponent on my left, we only won 402 out of 1,000. You can see the same information for tricks 2 through 5. We typically won a little less often in each case, except for trick 4, oddly. But you can see trick 1 is the one with the biggest difference. It would be nice to compare this to giving the 9 to the other opponent, but when I do that, I lead. Because I have the right, I lead it. So we win all 1,000 of the first trick in either case. The situations are fundamentally not comparable, but whatever. The conclusion of this is that giving the card to the opponent behind you is worse than giving the card to the opponent in front of you because of the impact of having that opponent behind you on the first trick. That's an interesting finding, but still the incremental impact of giving cards to either opponent is pretty similar ultimately. To make the comparison easier, graph 2 averages the opponents, and now graph 3 flips them to be on the same axis. It's understood the red bar opponents is bad, and the blue bar partner is good. But now we can see them side by side. So it looks like it hurts a bit more to equip your opponents than it helps to equip your partner. I suppose I can explain that too. If you call trump, you hopefully have a good hand. The 9 or the 10 or whatever you gave your partner is pretty likely to get overpowered by your trump cards. Of course, the same can be said for your opponent's card, but now they have a slightly higher ability to trump a non-trump card. This is all a somewhat educated guess at best, but the effect is small though. The only thing I don't like about this chart is the king column. Why is the king less impactful than the queen? Every other card follows a consistent upward pattern, but the king is not between the queen and the ace. The only thing I can think of is that each bar reflected here is a different combination of hands, and those circumstances are such that the impact is smaller. Not a great explanation, but this video is free, you know. Still, the difference amounts to about 1/10 of a point, not enough to fuss with, and the conclusion is that the impact is about 1/3 of a point for 9s, and a little more than 1/2 a point for aces, and in between for in between. Onward and upward. To quote Crosby, Stills, and Nash, "You who are on the road must have a code that you can live by." My code is I don't turn down bowers. This is one of those habits that seems reckless, but I actually think it might be optimal play. Table talk in euchre means talking in such a way so as to inform your partner's decisions, and that's illegal. But if you have a set playing strategy to play a certain way regardless of circumstances, that's fine. The purpose of this strategy is to ensure your partner never orders a bower into your hand, thus depriving you of the chance to go alone. For example, say that you do not follow this approach. I'm your partner, and I see my left 10 and a side ace, and decide that's very likely enough to win if paired with your right bower. I therefore order the card. Meanwhile, you would have had right ace, king 9, and a side ace, which is a good bet to win all 5 tricks by itself. If you always picked up bowers, I would have known to have passed, and this conflict would be removed, thus enabling you to go alone. Of course, if your opponents know this about you as well, they can sit on great hands and let you pick up the bower in a bad position. But the world is trade-offs, what can you do? My brother plays the same way, and the other day he turned down a bower for the first time that I can remember. His rationale was that he had a stronger hand of the other suit of the same color, and also had both of the off-color jacks. His logic was that it would likely get back around to him in the second bidding round. I probably would have picked it up, but I'm a simple man. More rock, less talk. Why do we care about any of this? I'd like to know the actual consequences of always picking up bowers. So I changed the parameters of the deal to always give myself the jack turn-up card. Instead of my usual 1,000 games, I bumped it to 10,000 because there are no permutations here, just this one configuration, and it won't take that long. Here are the results. If you pick up the right and have no other trumps, your expected points are indeed negative. But you still get euchred a bit less than half the time. That's a wild stat to me, as far as I can tell, it's just a combination of A, the guaranteed trick of the right bower, and B, a reflection of the fact that the other trump cards are distributed across 3 other players, which includes your partner. Going down the column, if you have one other trump card, the Euchre rate drops to 22% and your expected points flips to positive. And as you have more trump cards, your results improve, which all makes sense. Looking across the hands, the expected points is 0.65. So if you turn up a jack and everyone else knows to pass because you're going to pick it up regardless, your expected points is 0.65 before you look at your hand. And once you do, it follows the table above. Not too bad. Back in video 1, I talked about how there's a Euchre rule of thumb that says you can count on your partner for one trick. My goal here was to look across the universe of hands to see if I could confirm that the average tricks won by player 3, or your partner, is around 1. Unfortunately, it's not that simple. We can again look at boundary cases to see why. We established that the best 3-trump hand is right, left, ace, side, ace, side, ace. You don't need a lot of help from your partner there, and indeed, even if he tried, he probably couldn't win more than one trick because your hand is so strong. Meanwhile, on the weak side, queen 10, 9 side, 9 side, 9 needs a lot of help. So a single average of your partner's contributions across all hands is probably not that meaningful. But what's the point of this saying? What it means is that when you have a marginal hand and are trying to make a decision, you can assume your partner will win one trick. Therefore, the question is, can I win at least 2 tricks? With that context, it seemed clear what to do. I organized the hands by expected points. On the clearly losing side, we expect our partner to take more than one. On the clearly winning side, we are in command and our partner won't have as many chances to take tricks. The part we really care about here is the marginal zone of probably the right call but in danger of being euchred. Maybe I'm guiding this too much, but I really don't think I am. Filling in the column, we can see that expecting one trick from your partner on marginal hands is about right. If you've never played Euchre before, all this simulation and analysis may make you think it's an extremely complicated game. It's actually not at all. The rules are clear and the game is highly structured. I'm just 3 or 4 layers deep into this stuff. I think my dad's been bored with Euchre since the early 90s. Hell, I've been bored with Euchre since college, and the only reason I'm unbored with it now is because of this project. One thing you'll quickly find is that the cards you are dealt is the single most determinant factor. There are good decisions and bad decisions. The whole point of this video series is to elucidate that. But if you have bad cards, there's really nothing you can do about it. As I mentioned in video 1, all players must follow suit. If a diamond is led and you have 1 diamond, you play that diamond, no exceptions. The worst hands are ones for which you don't have many trump cards, but also having 4 suits can be particularly miserable. Whatever is led, you have to play a given card, thus limiting your ability to trump in and impact the game in any way. So following suit is restrictive and annoying, and this side view aims to answer a simple question. How often does a Euchre player follow suit? I've yet to discuss the so-called decision scorecard. I included code that saved this scorecard for every simulated hand. At first, I was just trying to make sure that my decision programs were working as intended, but later I realized it had other applications, and this is one of them. In every decide program, the machine determines a card to play when certain conditions are met. All this decision scorecard does is save a record of which decision was made. So in decide second player, decision 3bi_1 is I don't have any of the led suit, trump was not led, I have trump, and the next player is out of trump. In each of decide 2, 3, and 4, there's code that says if I only have one of the led suit, play that. In fact, that's decision number 1 in all 3 cases. Basically, if there's only one legal move, do it and spend no more time thinking. All I had to do was the following steps. 1, restrict to just tricks 1 through 4. I eliminated trick 5 because you only have 1 card left at that point, and therefore you don't really make a decision per se. And 2, count how many times we play the only card that follows suit, or the decision made is decision number 1. And that's all I had to do. Turns out it's 36.7% of the time. So just over a third of all decisions, if someone else leads, you'll be forced to play a given card. There's definitely a statistically rigorous way to evaluate this, but I just ran a bunch of simulations and looked at the graphs. I know I said I don't like graphs, but in this case I admit they're kind of helpful. This is right queen 9 side ace side queen. The red line represents the average of all available games, i.e. the rightmost point. The black line represents the cumulative average to that point. For example, if I'd run 500 hands, the answer would have been just above the 1000 simulation number. And finally, the blue dots represent the average of the 10 deciles, in this case, 100 games at a time. So this is interesting unto itself and shows that after a few hundred games, the average is fairly consistent. For this hand, I did a side run for 10,000 hands, and that result is expressed here. As you can see, the number moves a bit, but 6/100ths of a point's no big deal. And here's a weaker hand, the Queen 10 9 side 9 side 9 that we've already seen. This one was interesting because I seem to have gotten lucky early on in the first 1,000 hands. You can see that if I'd stopped at 500 hands, I would think this hand is stronger than it is at 1,000 hands. And here's the graph at 10,000. Fortunately, the answer for 10,000 ends up being extremely close to 1,000, so those few hundred early games were an outlier. But 2 hands out of 1,000 is not proof of anything, but I think about the concept of materiality. When something is material, it means that treating it more rigorously would cause the user to make different decisions. A few hundredths of a point isn't enough to change my interpretations of the hand, so I declare this good enough. I learned a lot with the simulator, and I'm reasonably pleased with what I found. I think my biggest miss was on going alone. This type of question is perfect for simulation. So you have right king, queen 9, side king. It's a very strong hand, 4 trump cards including the right bower, and a side king. Should you go alone or not? The question in mathematical terms looks like this. When I look at right king, queen 9, side king, I don't have a good feel for it. And lead definitely matters too. Having it would help and not having it would hurt. So when I started coding the alone gameplay, I increased the sophistication significantly. All 3 players make different decisions when someone's going alone, and I wanted to reflect that. But it didn't take me long to realize that my comparison was flawed. Even if I could code the alone gameplay perfectly, I've proven that the normal comparison basis can be off by a couple tenths of a point. On borderline calls like the above hand, that's enough to make the comparison unusable. So I could either quadruple the base gameplay code and then do the same for alone, or I could make a strategic withdrawal, and I chose the latter. But you came here for guidance, and my guidance on alone is as follows. Hell yeah. That's dumb. I realize that's not helpful. Thus concludes the Euchre Simulator project. I may have another dumb project at some point in the future, so check back circa 2024 or thereabouts. Until then, thank you very much for watching.